table. We have our table, our reference table. We'll be referencing to it anytime we need it. Now let's go through the paper. So question 1 says prove the identities. You can ignore it. You're not going to do this. Okay. It's not part of your scope. Now let's start with question 2, right? Question 2. Question 2 is now going to say, show that f of x equal to modulus is not differentiable at this. So we can just say f of x is not differentiable. If they say not differentiable, we need our piecewise function. So how will we do it? We know how to check something if it's not differentiable or differentiable. We differentiate, right? Then we look at the derivative when it is less than a certain value. Like here we have at x equal to 0. So when x is less than 0 and when x is greater than 0. So how do we do it? First, let's define this modulus. So we can have f of x is equal to, first you can say f of x is equal to modulus of x, which means if we were to define it, we'd say f of x is equal to, now we do it like this. It is equal to x, then that is if the thing inside is greater than 0. If x is greater than or equal to 0. And it is going to be equal to minus x if x is less than 0. Remember, this is so easy because we know that the modulus, its job is to keep things positive. So if something is going to be already, if this is going to be already positive, then it doesn't change. But if x is going to be less than 0, then it will put a minus outside. This is what we are saying, to keep it positive, because this x will be negative itself, and with this negative it is minus, which makes it plus. So that's just what it happens. If x is less than 0, you put the negative. That is, if the thing inside is less than 0, you put negative outside. If the thing inside, which happens to be x, if it's greater than 0, then you don't put a negative outside. Now once we have this, we have our piecewise, and we can now test for differentiability. We can say when x is greater than or equal to 0, we can say f of x is going to be equal to f of x is equal to, when it's greater than or equal to 0, we take this. F of x is equal to x, which means f prime of x is equal to 1. Now we can say let x be equal to 0, because we're checking differentiability at x equal to 0. You now find f prime of 0, it is still 1, because there is no x to put the 0 in, okay? Then we skip 2 lines. We now say when x is less than 0, your f of x is going to be equal to the bottom thing here, which is the negative x. Where f of x is equal to negative x, which means f prime of x is going to be equal to minus 1, which means you now say, if you say let x be equal to 0, you now find f prime of 0 is still minus 1. Now here you can say, since f prime of 0, when x is greater than or equal to 0, is not equal to f prime of 0 when we can say when x is less than 0, then we can now say therefore when x is less than 0, or if x is less than 0, so you can now say therefore the function is not differentiable. You can go and check the video on differentiability, the summary, if you have forgotten this. Differentiable at x equal to 0. This is going to be the final solution, and we are done. That's how we do it for this differentiability. We just check the derivative when x is greater than 0. It should be equal to the derivative when x is equal to 0. When you put the point which you are checking differentiability at. If we're checking differentiability at 1, we would find f dash 1. Then we'd find f dash 1 here and see if they're going to be the same. But here we are checking differentiability at x equal to 0. That is why we did that. So we'll be done, and we can go on to question 3. Goodbye for now.